All right, so some good news and bad news. In the last video, we learned about this thing called the product rule. The bad news is that's not the only rule that we learn in this section of videos. The good news is I think I'll be able to teach you the quotient rule significantly quicker than I taught you the product rule. The reason why is in that product rule video, well, first off, I reviewed a bunch of stuff from the previous section, but also I spent a lot of time trying to show you the theory behind the product rule, proving to you that the product rule works. It's something that I was supposed to do in this class, but not something you should expect to ever be tested on, at least not in this class. So often students don't really like it when I do it. Well, good news, for the quotient rule, I'm not going to prove anything to you at all, at least not yet. Because it'll turn out that in a few sections when we learn the last of our major rules, this thing called the chain rule, we'll be able to come up with the quotient rule pretty easily from the product rule and the chain rule. So for now, what I'm going to do is just tell you that there's this thing called the quotient rule, it exists, and I'll ask you to trust me that this ugly mess of symbols right here is that quotient rule. What the quotient rule tells you is when you're taking the derivative of a quotient, in other words, something divided by something, what you do is take the derivative of the top, the thing we're calling f of x, and multiply that by the bottom, g of x. Not the derivative of the bottom, but the bottom itself. From that, we want to subtract the derivative of the bottom, the derivative of the g of x, times the top, the f of x. You might see some similarities between the numerator of the quotient rule and what we developed in the last video, this product rule. In fact, it's almost identical. The only difference is we change from a plus sign here to a minus sign, and we define the functions f and g a little bit differently. For the quotient rule, it's f divided by g instead of f times g. But otherwise, what you see as the product rule is identical to what you have in the quotient rule, except for the sign in between the terms. And the fact that the quotient rule has a denominator. Once you do all that calculus up in the numerator, you're not done. You still have to divide by the g of x, the denominator of the original thing we're taking the derivative of, squared. No derivatives down here in the denominator, just the function g of x squared. This is the quotient rule as you typically see it written in a book. However, I'm kind of partial to this form, some shorthand, that says the exact same thing. F and g are assumed to be functions. The quotient of f and g, if we're taking the derivative, is equal to the derivative of f times g minus the derivative of g times f divided by g squared. Be nice if you could reconcile the blue box and the red box. With this rule, we can take derivatives of things that kind of look like fractions that are quotients, like the derivative of the natural log of x over x squared, for example. If we're taking the derivative of natural log of x over x squared, think the f of x is the natural log of x, and the g of x is the x squared. So we just plug things into this formula. We got the derivative of the top, the natural log of x, times the bottom, the x squared, minus the derivative of the bottom, the x squared, times the top, the natural log of x. But then don't forget, we're not done. We still have to divide that whole thing by the bottom, x squared in this case, squared. Much like the product rule, you can often go without this step, at least for these easy problems that I give you at the start of the section. But I'd encourage you to write this step because what you'll see is when we get to more complicated examples, like we will later in this section, you'll really want to show these different steps. So it's good to develop the good habits. The derivative of the natural log of x is just 1 over x. We have to multiply that by x squared. Note, not the derivative of x squared, but just x squared itself. From that, we want to subtract the derivative of x squared, which is 2x, times the natural log of x. That whole thing has to get divided by x squared squared, which means x squared times x squared, which is x to the 4th power. At this point, we don't have the d over dx symbol written anymore, so we're done with the calculus. Although I'd argue that we should probably clean this up a little bit. Fractions inside fractions are kind of ugly for one thing. The 1 over x times x squared is just equal to x. This x and one of these x's cancel. And from that, I want to subtract 2x natural log of x divided by x to the 4th power. I'd argue that this is a perfectly acceptable answer. However, it's worth pointing out that each of the terms up in the numerator have an x in them. So I could factor out an x from each of those terms and cancel it with an x in the denominator. And that would give me 1 minus 2 times the natural log of x divided by x cubed. Either answer is fine, although I think this one's a little bit better. That is the quotient rule. You might notice that I wrote above that we could actually do this specific problem without the quotient rule. We could use the product rule for this specific problem. And you're like, what? That doesn't make any sense. This ain't a product of two things, it's a quotient of two things. True, when it's written in this form, it's a quotient. But if you're really good with your algebra, you might recognize that we could rewrite the natural log of x divided by x squared as the natural log of x times x to the negative 2 power. Taking advantage of negative exponents like this changes a quotient into a product, so we could take this derivative without ever using the quotient rule. be the derivative of the natural log of x times x to the negative 2 power plus the derivative of x to the negative 2 power times the natural log of x. When we take this derivative using the product rule, the derivative of natural log of x is 1 over x. So I get 1 over x times x to the negative 2 power. Kind of weird to have x's in the denominator and have negative exponents, but we'll clean that up in the next step. Plus the derivative of x to the negative 2 power. I bring that negative 2 down in front and subtract 1 from the exponent. So I get negative 2x to the negative 3. So I could add negative 2x to the negative 3. In other words, subtract positive 2x to the negative 3. And then don't forget to tack on this natural log of x over here. If we wanted to write this without negative exponents, you could think about this as 1 over x squared. And 1 over x times 1 over x squared is 1 over x cubed. Similarly, you could think about this x to the negative 3 as 1 over x cubed. And then 2 times the natural log of x times 1 over x cubed could be rewritten as 2 natural log of x divided by x cubed. You might recognize that you have two fractions that have the common denominator. So if you felt the need, you could make this a single fraction by subtracting the numerators and dividing that by the x cubed, and that produces the exact same answer that we have over here. The point that I'm trying to make here is if you really didn't like the quotient rule, if you didn't like this new rule and didn't want to do things this way, that's okay, you don't need to. You just have to be good with your algebra. You just have to rewrite this quotient as a product, and then you can just use the product rule. You're like, yep, that's the one for me. I hate the quotient rule. I never want to do this the red way. I only want to do it the purple way. Well, bad news. While we can rewrite any quotient of products, sometimes doing so will leave us with something that we can't take the derivative of. For example, suppose we were trying to take the derivative of x squared divided by the natural log of x. If you really want to use the product rule, what you'd have to do is rewrite this as the derivative of x squared times the natural log of x raised up to the negative 1 power. The problem is we don't know the derivative of the natural log of x to the negative 1 power. So while the derivative of this is equal to the derivative of this, we kind of get stuck here. We can't go any further because we don't yet know how to deal with this second half of this product. The good news is we don't have to use the product rule because we have this quotient rule. So instead of worrying about how to rewrite this using the product rule, just use the quotient rule on it. We'd say that the derivative of x squared divided by the natural log of x is the derivative of the top, the x squared, times the natural log of x minus the derivative of the bottom, the natural log of x, times the x squared, all divided by the bottom, natural log of x now, squared. The great thing here is that d over dx's are all things we can deal with. We know the derivative of x squared, we know the derivative of natural log of x, so it's just a matter of taking those derivatives and simplifying. The derivative of x squared is 2x, so over here on the left I got 2x natural log of x, and from that I want to subtract the derivative of the natural log of x, which is 1 over x, times x squared. 1 over x times x squared is just x. I can cancel out the x in the bottom and one of the x's up top. So I get 2x natural log of x minus x divided by the natural log of x squared. The point with this second example is don't be misled by the first example. Sometimes you can go without the quotient rule and get the exact same answer using the product rule. However, sometimes you have examples where when you rewrite them in a form to use the product rule on them, you're left with something that we don't yet know how to take the derivative of. Hence the need for the quotient rule. I've got 2 or 3 more examples I want to do, then I'll call this video good. This first one, the derivative of the natural log of x divided by x squared minus 5x. It's written as a quotient, so your first instinct is probably to use the quotient rule on it, and that's exactly what you want to do. The quotient rule tells us that the derivative of this quotient is the derivative of the top, the natural log of x, times the bottom, x squared minus 5x. Make sure you put parentheses around here because I have 2 terms. If you don't have the parentheses, only the x squared would get multiplied by all this stuff. But you have to multiply the entire x squared minus 5x by this stuff. From that, I want to subtract the derivative of that x squared minus 5x, the bottom, times the top, the natural log of x, and then don't forget to divide that entire mess by the bottom, x squared minus 5x squared. Problem went from relatively compact to kind of a big mess, but the good news is we've simplified the calculus. The only calculus that's left is this derivative, no problem, and this derivative, no problem. The derivative of the natural log of x is just 1 over x. So I got 1 over x times x squared minus 5x. From that I want to subtract the derivative of x squared minus 5x, which is 2x minus 5. Hopefully that's a one-step process for you at this point in the class, times the natural log of x. I'll divide that entire thing by x squared minus 5x. I guess you could clean this up a little bit. We could take this 1 over x and distribute it through these parentheses. It's tempting to think, well, why don't I cancel out this x squared minus 5x and one of these x squared minus 5x's? You can't do that because I have 2 terms up in the numerator, so they'd each need to have an x squared minus 5x if I wanted to cancel with one of these. They don't, so I can't. But I could distribute the 1 over x, which I would probably do because I don't like having the fractions inside fractions. So while this is equivalent to the correct answer, maybe a better correct answer would be to make this x minus 5 minus 2x minus 5 times the natural log of x, all divided by x squared minus 5x squared. If you felt the need, you could distribute the natural log of x through these parentheses to get rid of the parentheses. Make sure you also distribute this -1 if you did so. You could also expand the denominator here to get rid of these parentheses, although I don't know that either of those would leave you in a form that's any simpler than what you have here. The verb simplify is somewhat subjective, and I kind of think this is about as good as you're going to get your answer, so I'd probably stop right here. What about this example? If you stare at this example, you might think that I, your teacher, made a mistake, because you look at this and you're like, I don't see a quotient, I see a product. I should use the product rule, not the quotient rule. No. And the reason why is because if you were using the product rule, you'd have to figure out the derivative of e to the negative x power. And you, at this point in the class, don't yet know the derivative of e to the negative x power. That's going to end up involving this thing called the chain rule, which we haven't yet learned. So what do? You get really clever with your algebra and you rewrite this as the derivative of x to the 4th power divided by e to the x power. Because e to the negative x is the same as 1 divided by e to the positive x. And x to the 4th times 1 divided by e to the positive x can be rewritten as x to the 4th over e to the x. I think for most students, the hardest part of this problem is going from here to here. Once you have it written in this form, it's not too bad. Just use the quotient rule. You could probably jump straight to a step that kind of looks like this and cut out this step altogether, but I'd encourage you not to do that. Not necessarily for this example, but for the examples we'll do in the next video where it gets significantly more complicated and it really helps to show your steps. So develop the good habits even though you might not need them right now. This is the derivative of the top, the derivative of x to the 4th power, times the bottom, the e to the x power, minus the derivative of the bottom, the derivative of e to the x, times the top, the x to the 4th, divided by the bottom, e to the x squared. See if I can squeeze this in right below here. The derivative of x to the 4th is just 4x cubed. So I got 4x cubed e to the x is my first term. And from that I want to subtract the derivative of e to the x, which is just e to the x. So I got x to the 4th times e to the x is my second term. That whole thing is over e to the x squared, which I could rewrite as e to the 2x, but I'm not going to. I'm going to instead recognize that I have an e to the x in each of these terms up top. So I can factor out that e to the x and cancel it with one of these e to the x's in the bottom and make my final answer 4x cubed minus x to the 4th divided by e to the x power. Yes, you could factor out an x cubed from each of these terms up top, although I don't know if that's necessarily any simpler. I'd probably stop right here. The point of this example was just to show that sometimes you'll be given something that's not in a form that's immediately conducive to the quotient rule. It's kind of a common theme in this class. The algebra necessary to rewrite an expression into a form where you can use the rules that you have is super important and frankly pretty hard, arguably one of the hardest parts of calculus. Don't be too hard on yourself if you didn't think to immediately rewrite this as a quotient. You're not really expected to be able to do that until it's demonstrated for you. Now that it's been demonstrated for you, if you see a problem something like this, you might think in terms of the quotient rule. One more example, then we'll call this video good. I want to make the argument that this problem that we've already done before, 6 over x squared plus 2/3, could be done with the quotient rule. But you don't want to do it with the quotient rule. So be careful. We're learning these new rules, but don't just immediately put your head down and be like, well, quotients, I should automatically use this. Take a look at this and think about, could I, the student, rewrite this in such a way that it would be easier to take the derivative of rather than using the quotient rule? In this case, the answer is absolutely you could. You could rewrite this as the derivative of 6x to the negative 2 power plus 2/3. Written in this form, the derivative is pretty easy. We use our constant multiple rule and our derivative sum rule to say that this is 6 times the derivative of x to the negative 2 power plus the derivative of 2/3. You can use the power rule over here to call this negative 2x to the negative 3, and then multiply it by this 6 to get negative 12x to the negative 3, and then recognize that 2/3 is just a constant, so its derivative is 0, so my answer is negative 12x to the negative 3rd power. In other words, negative 12 divided by x cubed. This is a fairly easy problem if you do this conversion, if you rewrite this problem into a form conducive to our polynomial rules. If you don't, you use the quotient rule, you'll get the exact same answer. It'll just be significantly harder. Look what would happen. We take the derivative of the top, the 6, and multiply that by the bottom, the x squared. Subtract from that the derivative of the bottom, the x squared, times that 6. And then divide the entire thing by x squared. Hopefully you'd recognize that this is a constant and its derivative just goes to 0. But if you don't, you might be like, well, it's a quotient. It's 2 divided by 3. I better use the quotient rule over there as well. It would be the derivative of the top, the 2, times the 3, minus the derivative of the bottom, the 3, times the 2. And then don't forget to divide the entire thing by the 3 squared. If you're paying really close attention, you might notice that I made a mistake. I don't want to go back and re-record. The quotient rule tells me that I have to divide by the denominator of the thing that I'm taking the derivative of squared, which is why this wasn't just e to the x, it was e to the x squared. That's why this wasn't just 3, it was 3 squared. That's why this shouldn't just be x squared, it should be x squared squared. Anyways, at this point we go through and take derivatives, but note that a lot of stuff is just going to cancel out. The derivative of 6 is just 0, and 0 times x squared is just 0. So from this first term, I just get a 0. I need to subtract the derivative of x squared, which is 2x, times the 6, divided by x squared squared, which is x to the 4th power. What happens with this term? Well, the derivative of 2 is just 0, and 0 times 3 is 0, so I get 0 for this first term. From that, I want to subtract the derivative of 3, which is also just 0. 0 times 2, I get 0 minus 0 up on the top, and 9 down on the bottom. Over here, I have negative 12x over x to the 4th power. In other words, negative 12 over x to the 3rd power, if I cancel this x with one of these x's. Then over here, I got 0 divided by 9, but 0 divided by anything is just 0, so I get plus 0, which I don't even have to write. I end up with the exact same answer that I got this way, although I think most people would say that this is a little bit harder, unnecessarily tedious perhaps, than what we did over here.